Hey everybody, Trey here, and welcome to this Hurricane Chasing Foundations module here on Storm Chaser Coaching. I'm really excited to do this module for you guys. I know a lot of you out there are interested in chasing hurricanes, so we wanted to include some hurricane chasing content here in the Chaser Academy. This module is going to be broken up into three different sections. The first section, which we will discuss today, is going to be the basics of hurricane forecasting and the meteorology behind hurricanes. So that's going to include the formation process, the ingredients they need to survive and mature, and how they move about in the ocean. Then the next episode, we're going to discuss the structure of a typical hurricane, looking at things like the outer bands, the eye wall, different things that happen with the eye wall that can indicate strengthening or weakening, different overall structural changes and what they mean for intensity, and how you can look for those on infrared and visible satellite imagery. Then the final episode will be covering hurricane chasing, the process that I use when I'm chasing a hurricane, how I am able to prioritize safety while chasing a hurricane. And so hopefully that is going to be a well-rounded little primer for you for how to chase hurricanes, at least the skeletal foundations of chasing hurricanes. We will do lots more content in the future that's a little bit more in-depth on hurricanes and hurricane chasing, but this module should give you a good foundation on how to chase hurricanes safely and effectively. So without further ado, let's go ahead and get started. Let's start off with how hurricanes form. All hurricanes start off as tropical disturbances, areas of disturbed weather that can result from things like troughs sliding into the tropics, waves developing along frontal zones over the ocean, etc. Most Atlantic hurricanes start off as what we call easterly waves. Easterly waves are inverted troughs that move from east to west. So a typical trough, one that might induce severe weather across the U.S., as we know, is a downward kink in the height contours aloft. Now, the winds in the mid-latitudes here in the U.S. flow from west to east. So those height contours are, again, it's a downward kink in the height contour. So you get that kind of counterclockwise rotation, counterclockwise circulation in the winds associated with that trough. An inverted trough is just the opposite of that. It is a trough that's basically upside down. So here in the tropics, the winds flow from east to west. So an inverted trough is just an upward kink in the height contours. And again, remember that the winds are going from east to west. So you're still getting that kind of counterclockwise rotation in the winds. And so this is still considered a trough. It's just flipped upside down from what we would consider a normal trough here in the mid-latitudes. It's an inverted trough. Typically, these easterly waves develop as thunderstorm complexes in Western Africa. These complexes eventually kind of dissipate. The area of disturbed flow aloft moves over the Atlantic. Initially dissipates because of the cooler waters here along the western coast of Africa. But once they get toward the warmer waters of the open Atlantic, they start to intensify again and thunderstorms develop. Of course, these easterly waves are troughs. They're sources of lift, and with an unstable atmosphere due to the warm ocean waters of the open Atlantic, thunderstorms start to develop. Now, as these thunderstorms start to develop, they release what's called latent heat. Latent heat is just the energy that's released due to phase change. And in this case, it is the evaporation of all this warm water over the Atlantic that can fuel more and more thunderstorm development. And it kind of creates a cycle. Thunderstorms develop, more and more latent heat is released, and more thunderstorms develop. As this happens, the pressures start to lower in that area, and you get an area of low pressure that develops as the thunderstorm coverage increases. The Coriolis force, which is due to the rotation of the Earth, allows the storms to kind of rotate around the center of low pressure in a counterclockwise fashion. And as the pressures continue to deepen, you can get a tropical depression, and eventually a tropical storm, and eventually a hurricane, if the ingredients are there for hurricane maturation. Now, what are these ingredients for hurricane formation and maturation? Well, as we've already begun to discuss, we need warm water and a lot of it. Not only do we need sea surface temperatures to be quite warm, generally above about 80 degrees Fahrenheit, but we need those warm temperatures to extend quite a ways down into the ocean. This can be measured through a product called oceanic heat content. This is basically just an integration of the vertical temperature profile of the ocean from the sea surface down to the 26 degree Celsius isotherm, which is about 80 degrees Fahrenheit. So it basically takes into account the total amount of energy available for potential developing tropical systems. The higher the sea surface temperatures and the greater the oceanic heat content, the greater the reservoir of fuel available to any developing tropical systems is. And that the higher these values are, the better the chances are for hurricane formation and maturation. Remember that hurricanes are fueled by the latent heat release of evaporation from the ocean surface. So if you don't have those high evaporation rates that come from warmer waters, you're not going to have a very favorable environment for that latent heat release and therefore the formation and maturation of a hurricane. So again, you need lots of warm water at the surface, but also extending down well into the ocean. The higher the oceanic heat content, the higher your sea surface temperatures are, the greater the chances are for hurricane development. Related to this is a moist atmosphere. If you have lots of warm water, you're going to get a lot of that evaporation of those warm waters into the air, providing a lot of water vapor to the air and a deep layer of moisture in the atmosphere for these thunderstorms to feed off of. If you have, again, cold waters, or if you have some dry air intruding into the potential area of development aloft, that's going to thwart robust thunderstorm development around that developing low pressure center, and it's not going to be as favorable for hurricane development. Similarly, you need a very unstable atmosphere. If you have a lot of colder ocean waters, well, that's going to lead to quite a stable low-level air mass and inhibit thunderstorm development. But if you have warmer waters, that's going to lead to a much more unstable environment and a favorable one for hurricane formation. And finally, contrary to supercells and tornadoes, hurricanes need weak vertical wind shear, which is that change in wind speed and direction with height, to intensify. This might seem a little counterintuitive. We have a rotating storm system. Wouldn't you need wind shear for the storm system to rotate? That's not the case. Let me tell you why. Mid-latitude cyclones, which are low pressure systems that cause severe weather across the world, here in the United States as well, those are usually tilted with height. So the center of low pressure at the surface is going to be offset from the subsequent levels as you go up in the atmosphere. It's kind of usually tilted back toward the west or northwest just a little bit.
Hey everyone, the video you're watching right now is a preview of the content that is available inside of the Chaser Academy. The Chaser Academy contains full-length training modules, chase and explain walkthroughs, Q&A sessions, and much more. Click the link in the description and subscribe now.
Hurricanes are vertically stacked systems, so the center of low pressure at the surface should be right below the center of low pressure at the subsequent levels of the atmosphere as you go up. So it is, again, vertically stacked. Hurricanes need to be vertically stacked in order to intensify. Wind shear, whether it is the change in direction of the winds with height or increasing speed with height, that is going to cause a tilt in the system. And a tilted hurricane or tilted tropical cyclone is not a system that is going to be able to intensify as effectively as if it were vertically stacked. So vertical wind shear is a big no-no for hurricane formation. Tropical systems need very weak vertical wind shear in order to intensify. All right, now let's talk about what governs the movement of hurricanes. Hurricanes are self-propagating systems, meaning that just like supercells can persist for quite a while based on the dynamics within the storm and the dynamics surrounding the storm, hurricanes can do the same thing. It's that constant cycle of latent heat release via evaporation off the warm ocean waters that allows a hurricane to propagate for really an extended period of time until that warm water source is negated or there's some other environmental factor that impedes the progress of the hurricane. But the overall background pattern is what guides the actual movement and motion of hurricanes. And specifically, it's the winds in the mid and upper levels of the atmosphere, really 500 millibars and above, that dictate the motion of hurricanes. So that means that the locations of troughs and ridges are quite important in steering hurricanes. In general, over the Atlantic, we have a feature called the Bermuda High, which is a big ridge of high pressure, really a fairly permanent ridge of high pressure that is situated over the open Atlantic that tends to guide hurricanes and developing tropical systems to the west out over the open Atlantic, really especially those waves that come off of Africa and even the storms that develop in the Caribbean. They're going to be they're going to try to drift west around the base of this Bermuda high. And then as they reach the western side, those winds kind of turn out of the south aloft, and that is going to usually try to help them turn toward the north, and that's why we get quite a few landfalls here on the Gulf Coast, the east coast of the U.S., around the edge of that Bermuda high.